Hello, everyone. This is Yonggan from the Efficient and Intelligent Computing Lab at Rice University. Today, I will present our work, DepthShrinker, which is a new compression paradigm towards boosting real hardware efficiency of compact neural networks. We know that there's a growing demand to accelerate deep neural networks, or DNNs, on real-world devices, which needs to bridge the gap between the complexity of powerful DNN models and the limited resources on real devices. However, there's a dilemma between the recent trends of efficient DNN designs and modern computing platforms. In particular, modern computing platforms are equipped with increasing numbers of cores to favor a higher degree of parallel computing, while efficient DNNs often adopt lightweight operators, which cannot utilize the parallelism on commercial devices, leading to low hardware utilization, thus limited improvements in real hardware efficiency as compared to theoretical flaws. To this end, in this work, our driven question is, how can we build compact DNNs with boosted hardware utilization to harvest more parallelized capability of modern hardware? To tackle this question, we propose the DepthShrinker framework to shrink consecutive operations into one single dense operation for improving hardware utilization, thus fulfilling real device efficiency. To validate the real device efficiency of dense operators, we conduct real device profilings. In particular, for commonly adopted model families, we replace each of their building blocks by one dense convolutional layer with scaled channel numbers for ensuring the same flaws, and measure their throughputs on 3 kinds of GPUs, which cover both desktop and edge settings. We find that the dense counterparts lead to notably higher throughputs over the original network under the same theoretical flaws. Such an improvement is more notable on desktop GPUs than edge ones due to higher parallelism, aligning with our hypothesis. Driven by motivating real device profiling results, we propose the DepthShrinker framework. To compress existing efficient DNNs, our key idea is to remove the activation functions in one inverted residual block, which is one of the most commonly adopted building blocks in existing efficient DNNs, and shrink it into one dense conv layer. Here's an example for illustrating our key idea. If the activation functions between 3 convolutional layers are removed, the convolution operations can be shrunk into one single dense operation with improved hardware utilization. However, the research questions are which activation functions to remove and how to restore the accuracy after the removal. To tackle this, we propose DepthShrinker as a 3-stage framework, which first identifies redundant activation functions, and then removes it and fine-tunes the resulting network, and finally merge consecutive linear operations after convergence. In particular, our DepthShrinker identifies redundant activation functions via learning binary masks M on activation functions with an L0 sparsity constraint. To make the learning process differentiable, we adopt a straight-through estimator to approximate the gradients on the mask M. In addition, we share the mask M for all activation functions in one block and adopt a latency-aware decay on the mask N to penalize the importance of latency bottleneck blocks. More details can be found in our paper. We merge consecutive linear operations after fine-tuning, and one nice property is that the resulting conv layer is only determined by the number of input and output channels of one block. Thus, DepthShrinker can shrink the wide intermediate layers within inverted residual blocks, leading to more promising efficiency improvements. We conduct extensive experiments to validate the achievable efficiency of DepthShrinker on top of 2 model families and 5 devices, including both GPUs and CPUs. When benchmarking with SOTA channel-wise pruning methods for efficient networks, our DepthShrinker consistently achieves better accuracy and FPS trade-off across all the devices. In particular, our DepthShrinker shows better scalability to extremely efficient cases. For example, a 3.06% higher accuracy with 1.53 times FPS. When comparing with layer-wise pruning, our DepthShrinker can achieve much better accuracy on the large compression ratios, indicating that shrinking is a soft version of hard pruning and can better maintain the accuracy of compression. That's all for our presentation. More interesting experiments and ablation studies can be found in our paper. Thanks.